Hi everyone, this is Addison Alford from the University of Oklahoma. I was the 2013 Holling Scholar, and this is the presentation that was given at the University of Alabama at Huntsville, as well as the National Severe Storms Lab. I'll go over a brief introduction and background for the presentation, as well as the methods that we use to analyze the data, and I'll go over the results and the conclusions of the warning analysis and the radar analysis. So why do we need to discuss these warnings? Klockow and Pepler found that after April 27th, folks did not understand that a tornado warning meant they needed to take action. This, of course, can lead to increased injuries and fatalities. And if we can provide a more accurate warning system, then we can cut down on those injuries and fatalities and possibly spur more action out of the folks that normally did not or will not take action. And of course, this will all lead to a more weather-ready nation as set down by NOAA's long-term goals. The question that needs to be answered here is about the previous storm classifications. They were very broad, and a more robust classification system could lead to a better understanding of where the office is going wrong in its tornado warnings. What I mean by the previous classifications is the three classifications that tornadoes and warnings were classified as: QLCS, supercell, and tropical. These made up 229 warnings for QLCS and 417 warnings for supercells, which are both very broad areas and need to be re-examined further. QLCS tornadoes, they're very difficult for the radar operators to see as the mesovortex generates from the ground upwards, and there may be a stronger correlation with rear inflow jets and tornado genesis. So what we did for the classifications was divided it into these categories. However, I'll go over non-supercell line and marginal supercells in this presentation. We also used GR2 Analyst with archived NCDC data, as well as archived AWIPS data from the office. We used this to examine all 721 tornado warnings, and the storm data was found with the NWS verification website. What I mean by non-supercell line and marginal supercells: the non-supercell line category eliminated any of the transition modes, so we were able to focus on a more textbook QLCS. Marginal supercells generally had less than 55 dBz in reflectivity, as well as non-persistent rotation throughout their entire life cycle. And we used the reconstructed RHIs and GR2 Analyst to look at the rear inflow jet. The results that we got were 26.9% of non-supercell 26.9% of tornadoes were non-supercell line, with a false alarm ratio of nearly 76%. Almost 10% of all false alarms were also marginal, with a false alarm ratio of almost 100% and a POD of 10%. And there was only one tornado caught out of the 10 marginal tornadoes. Both of these are very large areas in the database, and they warrant more study since they make up such a large percentage of the false alarms. If you remove all 53 of the marginal supercell warnings, you can reduce the false alarm rate by almost 2%, and your POD would only reduce by less than 0.5%. Non-supercell line tornadoes, again, they have a very high FAR and low POD, and if you eliminate all the false alarms in non-supercells, the non-supercell line, then you would have a false alarm reduction of 4%, and if you combine marginal and non-supercell line, you would have a reduction of about 7%. On the radar side of things, this storm actually had a tornado on it. You can see very weak reflectivity and very weak rotation. And this storm seems to actually be a stronger storm with about the same rotation but stronger reflectivity. However, the one on the left actually produced, the one on the right did not. Non-supercell line tornadoes, in this case, you can actually see a descending rear inflow jet just behind the mesovortex. The mesovortex is below 10,000 feet, and you can also see maybe a hint at a rear inflow channel or rear inflow notch on the back of the reflectivity, on the back of the line. On the scan prior to tornado genesis, you can see an even stronger descending rear inflow jet. The mesovortex has also deepened to around 10,000 feet, and you can see a very strong gradient in reflectivity, which indicates a rear inflow notch. At tornado genesis, you can see a very strong descending rear inflow jet just behind the mesovortex. And you can see that the mesovortex has ascended past 10,000 feet, as well as the rear inflow notch has strengthened. A bit more difficult case, you can see a descending rear inflow jet just behind a mesovortex. You can see a hint at a rear inflow notch in reflectivity. And on a plan view, you also see generally almost no rotation whatsoever. At tornado genesis, and without a warning, this tornado touched down, and you can see that the mesovortex has deepened, yet the descending rear inflow jet has actually weakened. However, this is probably due to the velocities becoming perpendicular to the radar beam. And you can see an even stronger rear inflow notch. The rear inflow notch was not found in every non-supercell line tornado case. However, it was found in many of the cases. This example shows this was a correct example, and what I mean by correct is the office was correct in not warning this storm. However, I noticed that there was a possible hint of a rear inflow jet that was descending toward the ground. However, you can see that the rear inflow jet was it descended well behind the mesovortex, and the mesovortex is almost non-existent. This was a false alarm case. However, you can see that the rear inflow jet remains elevated and the mesovortex never ascends. So overall, if you look at all 68 QLCS tornadoes since October 2007, 76.5% of them actually had a defined descending rear inflow jet. One tornado did not, in a non-supercell line case. 61.3% of false alarms did not have a descending rear inflow jet. And if you consider both of the tornado cases and false alarm cases, there were cases which the radar did not allow us to identify it correctly, either due to the radar beam being perpendicular to the radial velocities, or the radar was just simply too far to see a descending rear inflow jet. This does, of course, offer more problems. However, there could be more study that could be done. So in summary, the reclassification that we did on the warning database allowed us to understand where Birmingham was going wrong in their warnings. The results of that allowed us to study the radar signatures of these storms more closely, and the marginal supercells yielded very weak reflectivity and weak rotation throughout their lifetimes, and a concentrated or localized descent of the rear inflow jet was found in tornado cases and was not in non-tornadic cases. So the conclusions from this, Birmingham can now use the new classifications to understand where they're going wrong in their warnings. The rear inflow jet signature could be used and will be shown in some, what are we going to call those? Forecasting cards? I don't know.
I don't know what to call that.
Oh well, I just won't say anything about it. The rear inflow jet signature could be used in operational mode. The plan view is slightly more complicated to look at, but that will be discussed later with Kevin and with the aid of several forecasting cards that Andy and I are coming up with. The reason that the rear inflow jet may have a correlation with tornado genesis is after it hits it, descends into the ground. Law of, oh god, what's the law? Conservation of mass. After it descends to the ground, conservation of mass says that that air has to go somewhere, and it could be responsible for actually deepening the cold pull after it descends into the ground, or it could enhance near surface vorticity and allow for greater convergence near the surface. The future work on this study should be done using either dual Doppler or continued examination of single Doppler analysis to continue to work on the descending rear inflow jet, as well as marginal supercell signatures. And marginal supercell signatures should be looked at for a tornadic versus non-tornadic signature. Thank you to Kevin and the entire staff at Birmingham. Your guidance was most appreciated throughout the summer. I'd also like to thank Andy, who was the other Holling Scholar for the office, Jim Ledoux at the National Severe Storms Lab, who helped Andy and I before we even got out to Birmingham, as well as the Ernest F. Holling Scholarship Program for giving us this opportunity. Thanks for listening. You can contact me with any questions at addisonalford@ou.edu.